Okay, good morning. Good morning. It's time to start with the lecture. So, any questions from last time? If you remember, on Monday we started talking about some new type of distributions, specifically sampling distributions, and these are distributions that are coming from the statistics that you can compute from a sample that you take from your population. And we specifically addressed one of them. We started looking at the sampling distribution of the mean of a sample, and we also talked about the Central Limit Theorem. So, as a matter of fact, we discussed Theorem 8.2, which basically states that if x bar, or your sample mean, is the mean of a random sample of size n, taken from a population, with mean mu and finite variance sigma square, these are numbers that are known from the population, then the limiting form of the distribution z, which is the standard normal, with mu parameters x bar minus mu divided by sigma over the square root of n, when n goes to infinite, is a standard normal distribution with mean 0 and standard deviation 1. So last time there was a little bit of confusion in terms of the parameters that we're going to use to estimate this z random variable for the standard normal. When we are addressing, or basically what the Central Limit Theorem is saying is, if you want to use the conversion for the standard normal, then you have to use this conversion now where you're addressing the sample mean as your random variable. So in order to avoid discussion and confusion, from now on I'm going to refer specifically to this statistic of this random variable z when we are addressing random variables related to the sample mean. So if we go back to the example that we discussed right here, instead of computing this sigma for the sample before, or in order to compute that z value, what I'm going to do is just going to go straight to the this. You can just say that this is going to be equal, z is going to be equal to x bar minus mu divided by sigma over the square root of n. We know the values for the x bar, 775. We know the population values mu and sigma. The only thing that is going to be different now is that sigma has to be divided by the square root of n. And this is because the Central Limit Theorem tells us that as this tends to infinity, the value will approximate the normal or the standard normal distribution. So if we solve this, then what you're going to get is the following. Z is equal to 775 minus 800 divided by 40 over the square root of n, which is 16, and this is equal to minus 2.5. So this is going to be equal to the probability of z being less than negative 2.5. And if you go to the table, that probability is 0.0062. So the chances are very small the chances of having a probability that a random sample of 16 volts will have an average life of less than 775 hours. Any questions? Okay, let's look at another example. So here we have an electronics company manufactures resistors that have a mean resistance of 100 ohms and a standard deviation of 10 ohms. The distribution of resistance is normal, and you need to find the probability that the random sample of n equals 25 resistor will have an average resistance less than 95 ohms. So again, this question is addressing the average resistance. So in this case, your random variable is the average of the sample. Okay, and we know that as n increases and goes to infinite, we can use the standard normal distribution following the Central Limit Theorem to find that probability. So we know that the probability we are trying to find is the probability of having x bar being less than 95. Okay, so again, our random variable is not x, our random variable is x bar. Is the sample mean, and that's our random variable. We can use the central limit theorem to find that probability, so z, or we can estimate z as x bar minus mu divided by sigma over the square root of n. So we know x bar, 95, mu is 100, sigma is 10, and our sample size is 25. So this is the square root of 25. So this is going to be equal to minus 5 over 2, which is minus 2.5. So in other words, we have the probability of x bar being less than 95 is going to be equal to the probability of z being less than negative 2.5. And if you still have your tables, you can find that probability from the table. Again, you're still using the standard normal distribution. So from the standard normal table, you can obtain that probability. But if you observe from the previous problem, we got the same value for z. So this probability should be equal to 0.0062. Any questions? Okay, I'm going to go do another example. In this problem, we have a traveling between two campuses of a university in the city via shuttle bus takes on average 28 minutes with the standard deviation of 5 minutes. In a given week, a bus transports passengers 40 times. What is the probability that the average, again, average transport time, that is our random variable, was more than 30 minutes? So if you were to state that probability, how would you state that? That's correct. So our random variable is x bar, and we are here more than 30 minutes. So that x bar is greater than 30. So again, we know the central limit theorem. We know that our random variable we're studying, and we are addressing in this problem is the x bar, is the sample mean. So we can use the standard normal transformation. It's the probability of z being greater or equal to x bar minus mu divided by sigma over n. And we know the value of mu is 28 minutes. We know the value of n as 40. And we know sigma is 5. So from here we have the probability of z being greater or equal to x bar 30 minus 28 divided by sigma 5 over the square root of 40. And this is equal to the probability of z being greater than 2.53. In this case, we need to find the complement because we know the standard normal table is going to give you the probabilities from left to right. So we need to use the complement less than 2.53, and this is 1 minus 0.9943, which equals 0.0057. Okay, so 3 examples. The last one with the probability greater than. The only difference is that we look at the complement in order to find that probability. But for all of them, we are using the random variable, or the random variable is the sample mean. So based on our knowledge of the central limit theorem, we know that we can use the transformation of the standard normal to find those probabilities. Any questions? Okay, so you know this topic is important. The next thing that I'm going to show you is a different type of problem. And in this one, we have, instead of just one population, we have 2 populations. So suppose that we have 2 populations. The first mean for the first population is mu1, and the variance is 6 to the square 1. And we have the same thing, but with different mean and variance for the second population. And we let the statistic x bar 1 represent the mean of the random sample 8 and 1 selected from the first population. We do the same procedure for the second population. We get a sample from the second population and we get a different x bar. And we call that x bar 2. We can say that about the sampling distribution of the difference, or what can we say about this sampling distribution of the difference of the 2 sample means for repeated samples of N1 and N2? So the interesting thing is that when you look at the distribution of that difference, the central limit theorem can be easily extended to the 2 population case. So we can use the central limit theorem and use the standard normal distribution to find the probability of the difference between 2 means, or 2 sample means, that are coming from different populations. Okay? So it's not like having, this is your population and taking 2 different samples, x1 and x2. We are saying that we have 2 samples and we take 1 sample from the first one and another sample from the other one. So this is population 1 and this is population 2. Okay, so we can extend and use the central limit theorem to find such probabilities. So this is theorem 8.3. If independent samples of size N1 and N2 are from two populations, discrete or continuous, which means mu1 and mu2, and variances sigma 1 square and sigma 2 square, then the sampling distribution of the differences of means x bar 1 minus x bar 2 is approximately normally distributed with mean and variance given these two equations. So the mean is here of the difference, and the variance of the differences is here. Hence, we can use the standard normal random variable using those parameters to estimate that C value. So our mean now is the difference between the means of the populations, and our variance is the summation of the variance. Okay? And we're going to use Z as stated here to find the C value from the standard normal distribution. So let's look at one example. Okay, so here we have an example of a jet engine. So the effective life of a component used in a jet turbine aircraft engine is a random variable that would mean 5,000 hours and standard deviation of 40 hours. And we know the distribution of the effective life is fairly close to a normal distribution. The engine manufacturer introduces an improvement into the manufacturing process for this component that increases the mean life to this value, 5,050 hours, and decreases the standard deviation to 30 hours. Suppose that a random sample of N1 equals 16 components is selected from the old process, and a random sample of N2 equals 25 components is selected from the new improved process. What is the probability that the difference in the two sample means is at least 25 hours? Okay, so now we are interested in seeing if the improvement is at least 24 hours for the means. And we want to find that probability. Okay, so we know how to compute the mean of the statistics of the difference of the means, and we know how to compute the variances. And we know how to compute the standard normal random variable based on those parameters. So what we have here is we know x bar 1 and x bar 2, and we know that the mu of x2 bar minus x1 bar is going to be equal to the difference of the means, which is 50, 50 minus 5,000. So this is equal to 50. Now we need to compute the variance for the difference. So the variance for the differences is the variance of sigma square of x bar 2 minus x bar 1. So this is equal to sigma square of 2 and 2 plus sigma square of 1 and 1. And from the numbers that the problem is giving us, this is 30 squared over 25 plus 40 squared over 60. And this should be equal to 136 hours squared. And this is hours. So we have the mean of the differences, and we have the variance of the differences. So now we can proceed and compute the z value. So z is equal to x2 minus x1 bar minus mu2 minus mu1 divided by the square root of this. plus sigma squared 1 and 1. So we know the denominator. We just have to find the square root of that, of this expression. We know this. So we have most of the parameters that we need. So this is going to be equal to z equals 25 minus 50 divided by the square root of 136, which is equal to minus 2.14. And the probability that we're trying to compute is the probability that those differences of that difference is greater than 25 hours. Right? So the question is asking, what is the probability that the difference in the two sample means is at least 25 hours? We can use the complement to compute this probability. So this is 1 minus the probability of x2 minus x1 less than 25. And this is going to be equal to 1 minus the probability of z being less than minus 2.14. You can find this value from the standard normal table. And if you solve this, you can double check this number. This should be equal to 0.9838. So the probability that the difference of the two sample means is at least 25 hours is very high. It's almost 100%. That makes sense? There was an increase in number of hours of 50 hours from the new process, and there was also a reduction in variability. So yes, the solution makes sense. Okay, so I'll give you 5 minutes to work on this program on your own. And if you get it right, you're going to work individually. If you get it right, then I'll give you a bonus point on the next exam. So you only have 5 minutes. If you don't have your tables with you, you can state the whole expression and let the expression at the end, with the only step that is going to be missing is just finding the value of z. So 5 minutes. Yes, sir. Yes, if you can put it in the spreadsheet, that would be great. So I'm going to collect the solution. And don't forget to put your name on it. Okay, 1 minute. These times solver, you can type your solutions to your map. Cheers. Too much time. Anyone else? Here. Here. Anyone else with the paper? No? Okay. So what do we have here? We have the difference of two sample means, right? And we know that the statistics of the difference of two sample means follows a normal based on the Central Limit Theorem. So we are interested in the probability of x1 minus x2 being greater, well, x bar 1 minus x bar 2 being greater or equal to 1, which is the same as 1 minus the probability of x1 minus x2 bar being less than 1. So we know how to estimate the z value. From the lecture we learned that z for this case will be equal to x1 minus x bar 1 minus x bar 2 minus mu1 minus mu2 divided by the square root of sigma squared 1 divided by n1 plus sigma squared 2 divided by n2. So you can do this two different ways. You can compute this up front, and then plug in the numbers. Or you can put all the numbers into the expression. You will get the same result. So this is going to be equal to z equals 1 minus 0.5 divided by the square root of 0.81 divided by 36. You have a question over there? No? Plus 0.64 divided by 49. And this is equal to 2.65. So this is 1 minus the probability of z being less than 2.65. And from the table, you get this is 0.004. Yes, sir.
One is from the probability that
The one is coming from the question that you need to answer. So what is the probability that at least that a random sample of 36 tubes from manufacturer A will have a mean lifetime that is at least 1 year more? So that probability has to be greater or equal to 1 year. That makes sense? Any other question? Okay, so this concludes the topic on the estimation of the probability of the random sample or the sample mean. So now we're going to transition to a different type of statistic, and these are sampling distributions for x squared, which is the sample variance. So we're going to look at the sampling distribution for the sample variance. So initially we started with the sampling distribution for the mean, or for the sample mean. Now we're going to study the sampling distribution for the variance, or the sample variance. So if an engineer is interested in the population mean, resistance of a certain type of resistor, then the sampling distribution of x bar will be exploited once the sample information is gathered. However, if the variability in resistance is to be studied, then the sampling distribution of the sample variance will be used in learning about the population variance. So this depends on what are your interests, or what type of statistic are you interested in studying based on your experiment. So if for you it's important to get more information about the mean, because most of the decisions are going to be based on that figure, then you can exploit the sampling distribution for the mean. But sometimes it's the variability what's more important. So for those cases, we can exploit the sampling distributions for the variance. So if a random sample of size n is drawn from a normal population with mean mu and variance sigma squared, we obtain a value of the statistic squared by computing the sample variance. So I have said this a lot of times in this class. I have seen that some of you have problems estimating or computing this statistic, the sample variance. You need to make sure that you know how to compute that, because we're going to be using it in this lecture. So based on this theorem, if the sample variance x squared is the variance of the random sample of size n taken from a normal population having the variance sigma squared, then this statistic called chi-square equals n minus 1 times the sample variance divided by the population variance, has a chi-square distribution with n minus 1 degrees of freedom. So what we are saying is we can compute a statistic based on the sample variance, and we can get a distribution for that statistic. And we can use that distribution to estimate probabilities based on the sample variance. Okay, and that statistic is the chi-square. It's computed as here, n minus 1 times the sample variance divided by the population variance. And then that statistic chi-squared has a chi-square distribution with this n minus 1 degrees of freedom. The values of the random variable x or chi-square are calculated from each sample by the formula n minus 1 times the sample variance divided by the population variance, which is the same as here. Okay. The probability that a random sample produces a chi-square value greater than some specified value is equal to the area under the curve to the right of this value. Again, the probability that a random sample produces a chi-square value greater than some specified value is equal to the area under the curve to the right of this value. So the probability of producing a value greater than this value is this area right here. This is the probability. And that probability is denoted by alpha. So in this distribution, we're going to be, instead of looking from left to right, we're going to be looking from right to left. Okay? So table A5 from your textbook gives the value of the chi-square for different values of alpha and different degrees of freedom. So I brought that table here. So I'm going to pass you a copy of that document so you can follow the rest of the lecture. So again, as I did for the other tables, for the normal and the binomial, if you can bring this to class, it will help you a lot. For the purpose of the exam, I'm going to provide you with the tables in the document. So this document has two tables. One is the chi-square distribution, which is the one that we are explaining right now. It also has the t-distribution, which we're going to discuss later. Anybody has a copy? Yes. Two more? Well, okay, so the chi-square there's something else that we need to add here. So 95% of the chi-square distribution lies between x of chi-square 0.9575 and chi-square of 0.025. So that basically is the area, you can say from here to here. So 95% will be within those things. Now, in order to practice with the table, please find the chi-square value with 7 degrees of freedom and an area of 0.05 to the right. So I'm asking about chi-square of 0.05 with b equals 7. So if you go to the table, you will notice that again, the table is going to give you the values from right to left, from here to there. And you're going to have two tables for the chi-square distribution. Again, this is page 2 of your document. On the top, the first row, you're going to have the values for alpha. Alpha is the probability. So in this case, it's 0.05. The first thing you're going to have to do is, for that first column, you're going to have to find the value of alpha. That's on the second table here. Once you find that value of the probability, now you have to go to the first column of each table and find how many degrees of freedom are you using for your experiment. In this case, we have b equals 7. For the degrees of freedom, you're going to search down until you find 7. And again, as you did for the other tables, the value that you're interested in is the one that intersects between column of the probability and the row of the degrees of freedom. So in this case, what will be the value of the chi-square? Value, again, correct, is 0.067. Were you able to find that number, all of you? Okay, so again, you have two tables. Don't get confused. The important thing is you need to understand that at the top, the first row will give you the probability, and that's the first thing that you need to find. Then you focus on the degrees of freedom. Okay, so let's look at one example for this. Yes?
That 14 is the area to the right of that.
That 14 is not an area. That 14 is, so if you look at this graph right here, that is basically telling you that 14 is your x value, or not your x value, it's your horizontal A6 value. So if this is 0.14067, then if you cut at 14.067, the area or the probability is 0.05. So the probability is alpha. So the probability is 0.05. That's the area that is shaded. That area is going to occur at chi-square equals 14.067. That's a good question. Okay, so the value of the chi-square is giving you a probability of 0.05. Okay? Now let's look at the example. So we have a manufacturer of car batteries, guarantees that the batteries will last on average 3 years with a standard deviation of 1 year. If 5 of these batteries have lifetime of 1.9, 2.4, 3.0, 3.5, and 4.2 years, should the manufacturer still be convinced that the batteries have a standard deviation of 1 year? Assume that the battery lifetime follows a normal distribution. Okay, so The question here is not regarding the average lifetime of the battery, is regarding the variability in terms of the standard deviation. So we want to know if that standard deviation of 1 really represents what's happening when you test those batteries. So for variability, we know we can compute the the sample variance, so variability. So the first thing you have to do first, find sample variance. And how do you compute the sample variance? Sample variance equals 1 over n minus 1 times the summation from I equals 1 to n of differences. This is xi minus x bar squared. Okay? So if we were to compute this for this case, we have 1 over, what is the size of our sample? It's 5, correct? So we have 5 minus 1 times 1.9 minus 3 squared plus 2.4 minus 3 squared plus dot 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 up to 4.2 minus 3 squared. Okay, so you have to do that difference. You have to square the difference of each operation. So that value, sample variance equals 0.815. So now we have the sample variance, and we know that we can use the statistics chi-square to find this probability. So using the sampling distribution of the variance of the sample variance, we know that the chi-square is going to be equal to n minus 1 times the sample variance divided by sigma squared. Okay, so we have all the information we need. We can compute the chi-square value. Again, n minus 1 is 4, so we have 5 minus 1 times x squared 0.815 divided by sigma, which is 1, and this value is 3.26. Okay, so we have our chi-square, or the computed chi-square for our experiment. Now, what we're going to do now is, you can see this as the test for the chi-square. What we're going to do is we're going to compare our computed value versus the critical value from the chi-square distribution. So if we are able to have a chi-square value that is within the bounds of the critical values of the chi-square, we can say that our experiment is, well, I will not say correct, is valid with certain probability. Okay, so let me show you. So this is our computed chi-square. .26. Now we know our n equals 5. We know we have n minus 1 degrees of freedom, which equals 4. Okay, and we're going to use these parameters to find some probabilities from the table. So again, we have the chi-square distribution. Here we have the values of chi-square. And we know that the area inside the curve is the probability. So what we're going to do is the following. We're going to establish some limits. And if our critical value, or the value that we computed for our chi-square, is within these limits, that covers 95% of the probability, then we can say that that statement is valid with 95% with a probability of 95%. Now, if it is out these limits, then we cannot make that conclusion. So, remember initially when we started discussing the sampling, the sampling distribution for the sample variance, we said that 95% of the chi-square is within alpha 0.975 and alpha 0.025. So what we're saying is, if this is 95% of the probability, if our chi-square is within the chi-square for 0.975 and 0.025, then if this 326 is within those bounds, we can say that our statement is valid. So let's find the chi-square for alpha 0.97.5. What will be that chi-square? And also what will be this chi-square? So if you use your table, we know how many degrees of freedom we have, and we know the probability for one bound and the probability for the other bound. So for 4 degrees of freedom and alpha equals 0.975, table. Yeah, I don't have any tables, but I have the number right here. So this is chi-square equals 0.484, and this chi-square equals 11.143. So our chi-square, or the computed chi-square, this one, is within this value and this value. So our conclusion the computed value with sigma square equals 1 is reasonable no reason to suspect that sigma is other than 1 year. Okay, so we compute our chi-square for our sample variance, and then we perform the test of the critical chi-square based on the computed values for the distribution. if our chi-square is within those bounds, that means that the statement that we are saying, we have no reason to say that that is not correct, because the variability is within those bounds. And we're going to see more examples about this type of problem. Any questions? Yes, sir.
Why did you choose 95%?
95%? Yeah, that's a value that you choose as an experimenter.
Okay.
So 95% is a high probability. You want to make sure you can increase that to 0.99.
Okay.
And make sure that with 99% probability that the values that year is within the bounds. So you can say with 99% confidence that your statement is true. Okay. Again, if you reduces the probability, then your bounds should be the other way around. Yes. So the higher the probability, the shorter should be your bounds. Okay. Any other questions? Okay. So we still have another statistic, which is the t-distribution. Okay, so earlier in this lecture we discussed the utility of the Central Limit Theorem in applications revolve around the inference on a population mean or difference of two population means. However, it was assumed that the population standard deviation is known. So far we are saying, okay, we're going to compute we're going to use the sampling statistic or sampling distribution to study the sample mean. But we know the population standard deviation. That was an assumption. What we're going to do now is we're going to relax that assumption and we're going to say we don't know the population standard deviation. And we're going to explain what we're going to do in such cases. So assumption solves in situation when the engineer is familiar with the system. In many experimental scenarios, the knowledge of the standard deviation is certainly no more reasonable than the knowledge of the population mean. Okay, so we're also going to extend our analysis for the case in which you don't know the population mean. But for now, let's focus on not knowing the standard deviation of the population. So often an estimate of sigma must be supplied by the same sample information that produces the sample average. So as a result, a natural statistic to consider dealing with the inference of mu is this t-statistic. Does this look familiar? Yes. Looks like z, the z value for the central limit theorem. But it has a difference. The only difference is that now we don't know the population standard deviation, and we're going to estimate that standard deviation from the sample. Okay? So if we know the population standard deviation, then you can use the z. But if you don't know that population standard deviation, then what we are saying is you can estimate that standard deviation from the population, and you can still use this t-statistic to find the probability. Okay, so this is a different statistic. This is the t-statistic. Okay, so in the sample size, if the sample size is large enough, say n greater than 30 or equal to 30, the distribution of t does not differ from the standard normal. So what we're saying is if you have a large sample size and you plot the probability distribution for t, the shape is going to be very close to the shape of the normal or the standard normal. Okay, so this is another theorem, 8.5, in which we say that we let z be a standard normal random variable and v a chi-square random variable with v degrees of freedom, if z and b are independent, then the distribution of the random variable t, where t is the statistic, is given by the density function right here. So I'm going to ask you to memorize this. The only thing that you need to remember is that we can construct a sampling distribution for t based on the statistic that we already learned, the z and the chi-square. Okay, and we're going to use this t statistic and the t distribution, which is this is the density function, to compute some probabilities for the mean, but for the case in which we don't know the population standard deviation. So let's say we have n random variables, independent random variables, that are all normal with mean and standard deviation sigma. We know we can compute the sample mean like this and the sample variance like this. Then the random variable t, as we stated before, has a t distribution with n-1 degrees of freedom. So what we're saying is this statistic t with the sample standard deviation has a t distribution. It's no longer a normal distribution or standard normal distribution. When you don't know the population standard deviation, you can estimate that population standard deviation using the sample standard deviation, and you can use the t statistic to compute the probabilities. Okay, so again, this is maybe easier than you think. The only thing that you need to remember are the details in terms of when you use which distribution. So if you remember, if you're dealing with the random variable for the sample mean, and you know the population variance and the population standard deviation, you know that you're going to use the z, or the standard normal. Now, if you're dealing with the variability, or the variance, right, instead of the sample mean, you only know one sampling distribution at this point, which is the chi-square. So you're going to be dealing with the chi-square. Now, if you don't know the population variance, then you're going to estimate that population variance. You can still compute the probabilities by using the t random variable, and you have a t distribution for that. So there's only 3 distributions, one for each specific case. Okay, so the t distribution of t is similar to the distribution of z in that they both are symmetric or bell-shaped about the mean of 0. The t distribution is more variable owing to the fact that the t values depend on the fluctuations of 2 quantities. What are those 2 quantities? So we have 2 estimators, or 2 parameters that are estimated, and that creates more variability. For the z, we only have x bar, but now we have 2 estimators that will create more variability in your statistic. Okay? Whereas the z values depend only on the changes in x bar from sample to sample. For the t statistic, we're going to have different x bars and different variabilities or variances for each sample. Okay, so it is customary to let t alpha represent the t value above which we find an area equal to alpha. Okay, so since the t distribution is symmetric about the mean 0, we have that t of 1 minus alpha equals minus t alpha. And that can be seen here. So t alpha is this area. T1 minus alpha is this area. That T1 minus alpha is going to be equal to minus T alpha. The T value is in the area of 1 minus alpha to the right, and therefore an area of alpha to the left is equal to the negative T value that gives an area of alpha in the right tail of the distribution. So in other words, if you find T of 0.95, that is the same of finding negative t of 0.05. And if you have t of 0.99, then it's the same of finding the negative of 0.01, and so forth. And if you look at your document, the tables that I gave you today, page 1 has the t distribution. Okay? So we have the chi-square and the t distribution. Okay, so let's look at this example that is basically to help you understand how to use the table. So the t-value with 14 degrees of freedom that leaves an area of 0.025 to the left and therefore an area of 0.975 to the right is. Can you show me which number is that one from the table? So what we are looking at is at t of 0.975. If you go to the table, again, follows the same structure as the chi-square. You're going to have on your first row the probabilities, which are alpha, and the first column is giving you the degrees of freedom. And the probability is found by finding the intersection of the probability you want and the degrees of freedom that you're studying. So if you notice, if you try to find that probability from the table, you will not have the value of 0.975. And that's why we are explaining you how to get the area from the two different scales of the table or the graph. So we said that 0.95 is equal to minus t of 0.05, which means that this t value is going to be equal to t or minus t of 0.025. And this you can find from the table. So if you have 14 degrees of freedom and a probability or alpha equals 0.025, what will be the probability? Or that t-value, I'm sorry. What will be the t-value? See, what will be that value is minus something.
Negative 2.155.
Correct. Negative 2.145. Anybody was able to find that number? You have to remember to use that negative value before the number. Okay? Okay, so the other example I have here is to find the probability of t being within negative 0.025 and t of 0.05. So if you look at the curve, again, this is bell shape. And you have an area of t 0.025 to this area. And then you have another area here, t of 0.05. So the question is zero. The question is, what is this probability? So that probability is this area here in white. Let me change that to another color. So that's that area, right? So if you know that this is a probability of 0.025 and this is a probability of 0.05, what will be this area? That's correct. So what do? You look at the complement, right? You have those two areas, you have to subtract those areas from 1. So this is equal to 1 minus 0.025 minus 0.05. And that is 0.925. So the probability of minus t 0.025 less than t less than t.05 equals 0.925. Okay, so I'm going to stop here. I'm going to post the homework for next week. That homework is going to be due on Wednesday. And we will continue with our material on this topic on Monday. Have a good weekend. Do you have the sign sheet? Where is it? Got it?